Fred and Francine were up late studying for their AP Physics 2 test. They both would like a cup of coffee. However, they made their coffee hours ago and now it's cold. Both of them want to heat their cup of coffee. Fred has a hot plate to heat his cup of coffee. Francine does not have a hot plate, but she has a blender. Who is going to be able to increase the thermal energy of their coffee? Let's look at Fred first. He's using a hot plate. He is transferring heat into the coffee. We use the variable Q to refer to heat. If we put energy into the system, we say it's a positive Q. When energy leaves the system, we say it's a negative Q. For Fred's case, he's putting energy into the system of the coffee. So Fred has an example of a positive Q, an increased heat. We know that thermal energy is directly proportional to temperature, and after being on the hot plate, the coffee's temperature will go up. Therefore, Fred increases the thermal energy of the coffee.
Yeah.
Francine is not applying heat. She is doing work on the system. Energy can be transferred into a system by doing work, and we abbreviate work with W. If work is done to the system, it is a positive W. That would be like the blender doing work to the coffee. So that is going to be an example of a positive W. If work is done by the system, it's going to be a negative W. That would be an example like if the steam from your coffee is turning a pinwheel, you are doing work out of the system. Work is being done by the system to turn the pinwheel. So that would be a case of negative W. But for her, she's doing positive W. The result of running the blender is that the temperature of the coffee will go up. If the temperature goes up, then the thermal energy increased. Also. So Fred and Francine both were able to increase the thermal energy of the coffee. Let's go back to our work energy equation from the first year of physics. The work energy equation says the change in the kinetic energy of a system plus the change in the potential energy of a system is equal to the work. We're going to modify this to include heat and energy transfers that involve heat. Now we've allowed for the change in thermal energy, and we sometimes write this as E subscript TH. We also write it sometimes as a U. That will be more common, but I'm going to start it with thermal energy plus kinetic energy plus potential energy. So we've just added thermal energy. And in addition to work, we now have heat that can be added to the system or that can leave the system. We are going to talk about thermodynamics, and that is the basis for this unit. Thermodynamics is a scenario when there is no chemical change or changes in motion, meaning that the kinetic energy and potential energy changes will be zero because there's no change there. But there are temperature changes, and that's what we're going to look at. Looking at just changes caused by temperature change gives us thermodynamics. When that is the case, we can simplify this equation to be the change in thermal energy equals the work plus the heat. This can also be written as, so the change in energy equals work plus heat. This is the equation that is on your AP Physics equation sheet. The first law of thermodynamics says, for systems in which the thermal energy changes, a change in thermal energy is equal to the energy transferred into or out of the system as work, heat, or both. And you could summarize it with this equation. And here's a chart to understand what is going on when we have a system and the environment acting on it. If work is done on the system, it's a positive W. If heat is added to the system, this will be a positive Q. Both of these are examples of energy coming into the system. If work is done by the system, it's a negative W. If heat comes from the system, it's a negative Q. And both of these are examples of energy coming out of the system. And any change in energy can be calculated using delta U equals Q plus W. And you use positive signs for energy coming in and negative signs for energy coming out.